So last time we were talking about, I just want to do a quick recap, 5-minute recap of last class and then move on. So last time we were talking about discrete distributions. Discrete distributions have probability mass functions, not probability density functions. A probability mass function has two properties that you should know. They are the following. Sigma p of xi is equal to 1. That means the sum of all the probability values should be 1. And p of xi should be greater than or equal to 0, i.e. probabilities are non-negative. We learned how to find the mean last time. E of x is equal to summation xi p of xi. You also learned how to find the mean of some other function. E of h of x is equal to summation h of xi p of xi. Remember that? Meaning x cubed plus 9, something like that. So if I wanted e of x cubed plus 9, this would be e of x cubed plus e of 9, where e of 9 is 9 because e of a constant is the constant. That's one way to do it. Or I could have said summation xi cubed plus 9 times p of xi. So find some column. When you have a column like this, xi, p of xi, you can find some other column, xi cubed plus 9. So let's say that these values are 1 and 2 with probability 0.2 and 0.8. I'm just making this up. You will find x cubed plus 9. So that's 1 cubed plus 9, which is 10. And this one would be 2 cubed plus 9, which is 17. So you would have 10 times 0.2 plus 17 times 0.8. And that is equal to e of x cubed plus 9. Follow what I mean? This times that plus this times that. That's what this means. Whatever function is here, find that function and then go multiply by the probability. Then we also learned how to find variance. Sigma squared x, which is variance of x, is equal to e of x squared minus mu squared. That's the shortcut formula. Remember that? And mostly we learned how to just stick it into the calculator, xi, p of xi. Put this into L1, put this into L2, and go stat, calc, one variable statistics on L1 and L2. And basically it will give you x bar and it will give you sigma. And so you can get your answers very quickly instead of having to do these. You remember all that? Okay. What if I had two different variables, x and y? Let me just go over a couple of rules. E of 3x minus 4y and variance of 3x minus 4y. What would these be, do you think? Remember we had a rule for e of ax plus b last time? So I want to use that. Couldn't I go like this? E of 3x minus e of 4y, which is equal to 3e of x minus 4e of y. Does that make sense to you? I'm just pulling out the constants, not doing anything crazy. It just went like this. For variance, we had learned last time that variance of ax is equal to a squared variance of x. Correct? So using that, I can say variance of 3x minus 4y is 3 squared variance of x plus minus 4 squared variance of y. So it's 9 variance of x plus 16 variance of y. Look what's happened. In the case of the mean, I kept the minus sign here. So e of 3x minus 4y is e of 3x minus e of 4y. But in the case of the variance, this minus gets lumped with the minus 4, which gets squared. And so the variance of a linear combination of two random variables will be the two variances stacked one on top of another. So the fact that there's a minus here doesn't cancel the first one out with the second. In fact, they stack one on top of the other. So the variance of the linear combination will be even bigger than any one individual variance. You see the difference? Just wanted to point that out because you might see that on your exam.
So what if you have like a plus 4? Then that will give you the same answer, wouldn't it? Because you're squaring it?
Yeah, whether it's plus 4 or minus 4, it would be the same. Yeah.
If it was just for like, 4y, it would just be 0, right?
Yeah. So this one would be 9 variance of x plus nothing, because the variance of a constant is 0. So there were 4 rules. You should put those on your cheat sheet. E of ax is equal to a e of x. E of b is equal to b. B is a constant. Variance of b is equal to 0. And variance of minus 3x is equal to 9 variance of x, because the minus 3 got squared. So out of everything that I said last time, I think this page will serve you best. It's just a review of each thing you need to know. Follow? Do you have any questions before I do something new? So today I want to talk about binomial distribution. Toss an unfair coin once. There are only 2 possibilities when you toss a fair coin. So one toss is called one trial. And there are only 2 possibilities when you toss a coin, heads or tails. If you want to follow in your class, in your typed notes, I am on page 6. So such a trial with exactly 2 possibilities is called a Bernoulli trial. So I'm here on page 6. Consider an experiment in which we toss an unfair coin. Each toss is called a trial. Every trial has 2 outcomes. When you consider a trial that has 2 outcomes, it's called a Bernoulli trial. So another example of a Bernoulli trial would be absent, present. Another example of a Bernoulli trial would be normal birth weight, low birth weight. Another example would be parked illegally or legally. You get it? Any trial where there is exactly 2 possibilities is called Bernoulli. If you have n independent Bernoulli trials, that makes a binomial experiment. So a binomial experiment is made up of n independent Bernoulli trials, such as 6 babies born on New Year's Eve. Every baby is a Bernoulli trial because that baby is either normal birth weight or low birth weight, or that baby is either male or female. So the fact that I have 6 independent births makes it a binomial experiment because I have 6, which is N, independent Bernoulli trials. And therefore, that's a binomial experiment. Are you with me? Yes, Bernoulli is one trial with 2 possibilities. Now, if you take N Bernoulli trials, every baby being a trial, that becomes a binomial experiment. Let's take another example. You apply to law school, you either get in or you don't get in. Let's say 100 people applied. So these 100 would be a binomial experiment because it's made up of 100 independent Bernoulli trials. Each guy is a trial that applied. Follow me? Okay, so let's begin with this unfair coin. Did I lose you? No. Okay. So let's begin with this unfair coin where the probability of heads is 2 9s and the probability of tails is 7 9s. Toss this coin, this unfair coin, 3 times. Find the probability of exactly 2 heads. So the probability of heads is 2 9s. So the first one being heads is 2 9s. The probability that the second toss is heads is 2 9s. And I want the third one not to be heads because it says find the probability in 3 tosses that you get exactly 2 heads. So the third one is tails. So heads, heads, tails. Am I done? Am I done? Is this the answer? No. Why not? Nobody said that the 2 heads have to come first and then the tail, right? What about this? Tails, heads, heads. Or what about heads, tails, heads? So there are different combinations, right? Such that I have 2 heads and a tail. So I have to take those into account. There are 3 such combinations with 2 heads and a tail. So that 3 comes from the fact that it's 3 choose 2. How many ways can I choose the 2 positions where the heads will go out of 3 positions? And 3 choose 2 turns out to be 3. So my total answer, my final answer to this problem is 3 times 2 9s times 2 9s times 7 9s. Because there are 3 different arrangements with 2 heads and a tail. Agreed? So this 3 comes from 3 choose 2, or N choose R. N is 3. R is the number of successes. So N is the number of trials. R is the number of successes. P is the probability of success, which is 2 9s. In this case, heads are regarded as successes. And Q is the probability of failure, which is 7 9s. And P plus Q add up to 1. meaning P and Q are complements. So here's the binomial theorem. It says the probability of R successes in n trials is given by n choose R, P raised to the R, Q raised to the n minus R. You've seen this before. I've talked about it before this semester, right? But this is the time to formalize it. So let's take another question. Let's say that I toss the unfair coin 5 times. What's the probability of 2 heads? So again, R is 2. That's the number of successes. And I'm calling heads a success because that's what they're asking about. R equals 2. That's the number of heads. I'm calling heads successes. N, of course, is 5 because I have 5 trials. And my answer is 5 choose 2, N choose R. P is 2 nines, that's the probability of heads. Raised to the 2 because I want 2 successes. So I raise the success probability to the 2 power and the failure probability to the rest of them. So 5 minus 2, which is 3. The calculator does this automatically for you. You don't have to do each piece separately. It does it by binomial PDF of N, P, R. So N is 5, P is 2 nines, and R is 2. And you reach this binomial PDF the same way you would reach norm CDF or inverse norm, by going second, distributions. Second function, distributions. Let me grab my calculator and do it for you. So second, distributions. Go down to binomial PDF. N is 5, P is 2 nines, and R is 2. 0.23235. Get it? So you don't have to sit there going NCR and all that. It just does the whole thing for you. So because it said exactly 2 heads, I'm doing PDF. If it said at most 2 heads, I would do CDF. Let me explain. If the question was, find the probability of at most 2 heads in 5 tosses. At most 2 heads. That means probability R less than or equal to 2. That means no heads, or 1 head, or 2 heads. I'm not going to do 3 different binomial PDFs. It's a waste of time. This is binomial PDF 5290 plus binomial PDF 5291 plus binomial PDF 5, 2 nines, 2. And I would have to put it in 3 different times in my calculator. That's silly. All this is summed up by binomial CDF. C for cumulative. N, P, 2. 2 is the last one. So it's saying take the probability of 2 and everybody that came before and add them up. That's binomial CDF. C for cumulative. Yeah.
What if it was asking like
At least? That's my next example. Any issue with this? Go get me an answer. Could you do this on your calculator? I'll do it also. Let's see. Second, distributions. Binomial CDF. That's the second binomial available to me. N is 5. P is 2 nines. Comma 2. 0.9236. So it took all these 3 probabilities and added them up, and that's how we got 0.9236. Is there any confusion? Please ask me, guys. Next example, probability less than 2 heads. Less than 2 heads does not include 2. This is a discrete distribution. Strictly less than 2 doesn't include 2. So this is equal to probability of 0 or 1. So this would be binomial CDF of 5, 2 nines, and the last one that you want to include, that's a 1. Get it? Let's get an answer. Second distribution, binomial CDF. N is 5. P is 2 nines. And 1. 0.6912. Next one, probability more than 2 heads. More than 2 heads. More than 2 doesn't include 2. More than 2 means strictly greater than 2. So probability R greater than 2. That means 3 or 4 or 5. Right? Who's missing? My calculator only sums up from some number down to 0. It doesn't go the other way, right? So here's the probability mass function. No heads with probability of 0 heads. 1 head, probability 1. 2, P of 2. 3, P of 3. 4, P of 4. 5, P of 5. All these guys add up to 1, right? I'm interested in 3, 4, and 5. This, and this added together. So my question is, who's missing? Because if certain ones are missing, I can take these guys away from 1. Right, 0 and 1 and 2 are missing. So how about doing this? 100%, that's this one, minus probability of 0, 1, and 2. Which is 1 minus binomial CDF, 5, 2 nines, and the last number that I want included is 2, so 2. I'm telling the calculator to go to the probability of 2, add up the probability of 2, 1, and 0, find that answer, and then I'm going to subtract that answer from 100%. So this is binomial CDF NP2, and I will take that away from 1 to get this, which is my answer. Follow me. So what do we get when we do that? Second distribution, binomial CDF of 5, 2 nines, 2, and I want to take that away from 1 minus the answer, 0.0764. Everyone okay? And the last one, probability at least 2 heads. At least 2 heads means 2 heads, or 3 heads, or 4 heads, or 5 heads. Because I have 5 tosses, right? So the maximum number I can have is 5 heads. Who is missing? 0 and 1 are missing. So 100% minus probability of 0 or 1. So 1 minus binomial CDF N P1. So when you encounter a binomial question, you should go through this. Just write it out like I did, because it'll help you think it through, right? At least 2 means 2, 3, 4, 5. Who is missing? 0 and 1, 0 or 1. And then take away 0, 1 from 100%. Question? Okay, so last time we had said that when we have a discrete distribution with some probability mass function, to find the mean E of x, which is the mean, which is mu, we can do summation xi p of xi. So when you have x1, p of x1, x2, p of x2, the way to find the mean is to take this times that plus this times that, because each outcome is occurring with a different probability, right? I no longer have to do this in the special case where I'm dealing with a discrete distribution which is binomial. So if I know, let me write it this way, all discrete distributions, this is what you use. But if I know ahead of time that it's special, meaning binomial, then I can cut to the chase. Because think how long it's going to take me to do this. This times this, 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 and this can go on for a big N, right? So instead of that, cut to the chase, E of x, which is the mean, otherwise known as mu, for binomial is just n times p. And you guys already do this in your real life. Let me explain. If I said to you, I have 200 kids in my class and 5% will fail, how many would you expect to fail? Wouldn't you do this? 200 times 0.05, which is 10 kids, will fail. What did you do? You took n and you times it by p, and that's how you found the expectation or the expected value, right? If I said there are 200 kids, how many kids are you expecting will fail? You will take n and times it by p. You already do that in your mind, intuitively. You do, right? If I said to you that your exam will have 100 questions and 3% of them will be difficult, how many do you expect to be difficult? 3% of 100, which is 3. n times p, right? So mu equals n times p. You should put that on your cheat sheet. And sigma squared, first let me write the formula that you learned last time for variance of any discrete. That was e of x squared minus mu squared. But you don't have to go through the trouble of all this. If you know that it's binomial, you can just do n times p times q. And therefore, the standard deviation, sigma, would be square root of n times p times q. Let's do an example. 1,000 people apply to a particular law school. Probability of getting in, 2%. Find the mean number who get in and find the standard deviation of people who get in. All you do is mu equals n times p. That's the mean. So 1,000 times 0.02 equals 20. So I expect 20 people to get in. And the next question says find the standard deviation. That would be sigma equals radical n, n times p times q. So radical 20 times 0.98. Radical 20 times 0.98. 4.43 is the standard deviation. Are you following me? Okay. Okay. On page 9 of your class, of your typed notes, I gave you an example to try, and I gave you answers on the bottom. So before you come back on Friday, I'm going to talk about other stuff, but I just want to make sure I get this in. Before you come back on Friday, would you try all the problems on page 9 in your discrete distribution lecture so that you yourself know if you need help with binomial or not, right? You should be able to do each of these questions. The answers are given on the bottom. So it'll be good practice for you. The next thing I want to mention is the concept of unusually large or unusually small. So let's say that n is 10 and p is 30%. Therefore, q is 70%. What's the mean? What's the mean? N times p, right? Which is 10 times 0.3, which is 3. Okay, so my mean is 3. The question is, would it be unusual to see 8 successes. Would it be unusual to see 8 successes? So let me put a context to this problem. Let's say that there are 10 healthcare workers exposed to a virus. N is 10. And P is the probability of developing a disease. Meaning you're exposed to this virus, but you get sick 30% of the time from this virus. And the probability of not developing the disease is 70%. Would it be unusual to see 8 people get sick? Now, of course, sickness is not a successful thing, but it doesn't matter. You're assigning successes to whatever they're asking about. So would it be unusual to see 8 people get sick is the question. So getting sick would be deemed the success. Therefore, P is the probability of getting sick. Follow what I mean? So how do you answer a question like this? Would it be unusual to see 8 people getting sick? It's not what you think. It's not, you don't find the probability of 8 and answer the question that way. What you do is you find the probability of 8 or 9 or 10. We are talking p-value here, folks. Remember what the p-value is? Let me draw a picture and remind you. The p-value is the probability of being more extreme or equal to the test statistic. So this is saying if you observe 8 people getting sick, would it be unusual? I want to find the probability of 8 or more extreme than 8. That's why I'm going more in the right tail. I'm looking for the p-value. So if this p-value, I should write something here. So our successes are considered unusually high if the probability x greater than or equal to r is less than or equal to 5%. Put that on your cheat sheet. Our successes are considered unusually high if I find the probability of 8 or more, and if this number is really small, then that would mean that 8 is so far into the tail of the distribution that the probability of being even more than it is small, and therefore 8 is nowhere near the usual values. See, usual values occur here, right? Near the mean. Unusual values occur in the tail of the distribution. So if the probability of being 8 or even worse than 8 is very small, that implies that 8 is nowhere near the center. The probability of being worse than 8 is so small that 8 has to be somewhere in the tail of the distribution. And if you're in the tail of the distribution, then there's nothing usual about you. Get it? So we're saying if the probability of being even worse than 8 or equal to 8 is very small, less than 5%, then 8 is out here somewhere. And if you are out here, then you are not considered usual. So let's go find the probability of 8 or 9 or 10. Well, we know how to do this on our calculator, right? Probability of 8 or 9 or 10 is 1 minus binomial CDF NP7. Meaning I want to take away from 1 the probability of 0, all the way to the probability of 7. Let's do it. 1 minus second distribution binomial CDF of n, which is 10, p, which is 0.3, and 7. 0.0015. So this probability turns out to be less than 5%. 0.0015 is less than or equal to 5%. And therefore, 8 is indeed unusually small. I mean, unusually large. It's larger than the mean, so it's unusually large, unusually high. Yes. Zoom out. Let me focus it. So I kind of imagined that it would be too high because the mean was 3, right? And what was the standard deviation? I just want to see how many standard deviations it is above the mean, right? What's the standard deviation? Sigma equals radical NPQ. So radical 10 times 0.3 times 0.7. So radical 2.1, which is 1.45. So every standard deviation is 1.45, right? So if I start at 3 in a mound-shaped distribution, no one said it's mound-shaped, but you know, binomial tends towards normal when n is large, okay? So if I start at the mean, which is 3, and I go 1.5, 1.5, 1.5, 3 times 1.5 is 4.5, and 4.5 plus the mean is 7.5. So certainly, after 7.5, things would be considered very unusual, right? If I'm 3 standard deviations to the right of the mean. And 8 is more than 3 standard deviations to the right of the mean. So I would think that it would be very unusual. On the other hand, if the question was, would 5 successes be considered unusual? Would 5 people developing the disease be considered unusual? Let's do it. Next question says, would 5 be considered unusual? Unusual in what way? Unusually high. Why high? Because 5 is greater than the mean. That's why I'm considering it unusually high. It certainly can't be unusually low if it's bigger than the mean, right? Right or no? So would 5 be considered unusually high is the question. So I want the probability of x being greater than or equal to 5. Not just the probability of 5, but the probability of 5 or more. I want the p-value. Probability of 5, 6, ... all the way to 10. That's what I'm after. So this would be 1 minus probability of 0 through 4. So 1 minus binomial CDF NP4. N is 10, P is 0.3. So 1 minus second distribution binomial CDF 10 comma P, which is 0.3, comma 4. 0.15. 0.15 is not less than or equal to 5%. Therefore, 5 developing the disease out of 10 people would not be unusual. Unusual. Meaning, for something to be unusual, the probability of being more extreme than it on the right has to be less than or equal to 5%. And that's not the case here. Right? So if I were to draw a picture, I'm saying here's 5% alpha, and you're landing here because your p-value is 15%. That's what I'm trying to say. So there's nothing unusual about you. The test is not significant. Follow? Follow what I mean? Okay. We continue next time. There's hardly anything left to say next time. But we'll talk about unusually low, and then that would be all the material for the test. Does anybody want this? It's going in the garbage. Hi. Which one wouldn't be unusual? Five successes are not, where is the stuff for that? Yeah, I'm looking for it. Okay, so 5 successes are not unusual because the probability of being more than 5 is 15%. So if you're here and this area is 15%, there's nothing unusual about you because you need to be in the 5% tail to be unusual. Because that's how its p-value is defined. Okay, yeah.